algorithm, we figured out that it was a handy way of finding the min cut or max flow, where we were interested in particular in the pipes in our network of pipes here that were most likely to burst, the ones that were saturating because of the costs that were involved. Now, I've written up sort of what we're going to try to achieve today before we get to the lab. So the first point here is capacities are not equal to costs. Well, not yet. So all I've done here is shown you that there are given some capacities on our pipes. One can do augmenting paths to find the optimal cut through this graph. That doesn't yet necessarily mean that we're ready to plug in our problems where we have world states in either binary form or multi-category form directly into this mechanism. So that's what we're going to address right now.
Would that have been a source or a sink based on that?
Based on this cut, some of the nodes are now attached to the source and some are attached to the sink.
Yeah.
We're about to, in just 2 slides, I think, we're about to see what that means to the world state when we're trying to do graphs, trying to do not a posteriori inference on our graphical models. All right. So I wanted to just remind you, we're dealing with this situation where we have a black box that expects capacities, but given those capacities, once we give the capacities in the right format, graph cuts or augmenting paths, these types of algorithms can find for us an optimal solution. But it's up to us to convert what we've normally talked about as probabilities, right, or as potentials, or as equivalently as, what else do we call them? Not, we were trying to maximize probabilities or maximize potentials. Alternately, we were trying to minimize the costs. So now we've got to figure out, right, how do the two worlds relate? So we said, all right, well, we've got this world of unary costs and pairwise costs because we can figure out that we're either dealing with a world state and its associated data, or a world state and its any one of its neighbors. Let's just start off for now. We'll change this in a little while, but let's start off for now and say, okay, there's going to be a pairwise cost for putting 2 nodes together which both have world state 0. The cost is going to be 0. In other words, it's a very cheap cost. Similarly for putting 2 1s next to each other. But putting a 1 next to a 0 has some non-zero cost. Right? So this is going to be our initial setup. We saw this slide. This is where we stopped on Tuesday. We said, all right, we're going to make as many nodes here in the middle as there are pixels. Each one is going to have some discrete number of world states. For now, we're just going to deal with this as a binary problem. And we're going to attach source node to each of these, and we're going to attach each one also to a sink. So we've got little arrows going from the source into node number 3, and then you've got another blue edge coming out of node 3 going into the sink. So far, we're working towards making our conditional independence network of pixels, at least in the shape of something that we can hand to our max flow min-cut solution. Now we have to talk about what we do in terms of the capacities. So we're going to add the capacities in the following way. We're going to, for now, we're going to say, all right, so I'm not going to pull the rug out from under you. We're going to build up the solution in steps, right? So for the simplest case, this is what it looks like, but then we will have to make it a little more complicated. So please be prepared that this isn't the final answer. This is a good intermediate answer. All right, so we're going to put on this edge here, we're going to put the unary cost of making pixel A state 0. And on this blue arrow, we're putting the cost, the unary cost of making pixel A a state 1, W equals 1. Right. This part is going to be slightly counterintuitive, which is why I really need you to pay attention for the fact that the 0 is up here and the 1 is down here. I'll show you in the next slide the trickiness of it. For now, it should be okay, right? We've got a unary cost for two things that might happen to A. You can already tell, and you've seen this in graph cuts, we're probably not going to cut both of these, right? Because then we'd be cutting off A from both the source and the sink, and that's no good, right? We're going to cut off the flow so that A is attached to one or the other, but it's attached to one of them. All right, so that's our unary costs, similarly for B, similarly for C. Then we have pairwise costs, and if you ever get confused about this, just keep in mind, between nodes A and B, you're going to have an arrow going from A to B. So that arrow is looking at the pairwise cost of A and B being in configuration 1 and 0. Obviously, for the other arrow, it's going to have to be the other way around. So that's for A being 0 and B being 1. Similarly between B and C. So far, shouldn't be so bad, right? We've just transposed. We've transferred our costs, unary and pairwise, that we know we wanted to enforce into our graph construction. All right. Now, what does that look like in practice when we actually do a cut? So this is the part that's going to be slightly tricky. These were the let's just say we found, after running augmenting paths, we found that this was the pipe that was most likely to burst. So was this one, so was this one. Augmenting path stopped because at that point there was no more capacity for flow. There's no opportunity to find any other pipes that might saturate. These are the pipes that will saturate. So this is the optimal solution. But what does that optimal solution mean to us when we have 3 pixels, A, B, C, and we just want to know whether they are 0, 0, 1, 0, 0, 0, or what combination of zeros and ones for these 3 random variables. Because the cut was like this, you can already see the solution here. Because the cut was like this, what that means is we've paid the cost. We've paid the unary cost of making A 0. If you bought the ticket to see that movie, then that's what you get. You've paid the cost of A being 0, so this is now a 0. I know it might be slightly counterintuitive because you're thinking, well, hold on, no, you've cut up here, so surely A is now attached to the sink, which would be a 1. No, it's because you have to look at what price you've paid. You've paid the price of a unary cost. Which unary cost? The unary cost of making A have W equals 0. Similarly for B, and similarly for C. So the solution is 0, 0, 0 for the 3 pixels, and the cost we have paid, the total cost we have paid so far, is unary A of 0, unary B of 0, and unary C of 0. The ones corresponding to those 3, i.e. these 3 right here. Yes?
Yeah, so from A there goes a PAB 10.
PAB
10, yeah.
10.
Why is that 1 to 0 if we pay the cost of 0 to get to A?
We've paid our unary cost because we cut this line.
Yeah, so we set A to 0.
So A gets a 0, indeed.
And then, why, if we go to B then, why is it P10 and not 01?
Why is P? Say the question again.
So PAB 10.
Yes.
Does that say that we go from state 1 to state 0? Or value 1 to value 0?
If we don't saturate this edge, if it is not part of the graph cut solution, then we don't pay that penalty. We don't incur PAB 10.
I understand. No, sorry. It's more a question to the previous slide. Why is that denoted 10 and not 01 if A has value 0 in that case? Why are the right arrows 10 indexed and why are the left arrows 01 indexed?
Okay, so I think we're talking about a notation question, essentially. So these, we're saying PAB. So I'm going to be talking about, so the first argument that's going to go in here is what is a possible state of A, and the second one's going to be a possible state of B. So as long as we write it PAB, then I have to represent with my arrows both the configuration of A being 1 and the configuration of A being 0.
Okay.
And for B, I always have to have the opposite.
Okay. But there is a 0, 0 version too then. Which is
This
0.
is why we said for now.
Okay, okay.
You're absolutely right, but you're giving away the game for some slides that are coming up. For now, we said PAB00 is 0.
But it's there, it's just 0 now.
It's just 0 now. Yes, that's exactly right. And because we paid for A to be 0 and we paid for B to be 0, because that's our, we paid for A to be 0 and B to be 0 by going through here, we never had to cut either of these edges. Because that's 0 and that's 0, these pairwise terms don't apply. Okay. So this is the way to read it, right? If someone hands you a picture like this and says, okay, what does that solution mean? You're supposed to look at it and say, right, what costs have I paid? I've paid this cost to make A a 0. And that's what goes here. All right. Am I the only one who was confused by this the first time I saw it? I mean, maybe I don't want to suggest confusions that aren't there. To me, this sync being here connected to the A was slightly tricky. So I'm pointing it out. Don't get sidelined by that. But maybe I'm making it worse. All right, a different cut. You throw it into augmenting. You throw your problem into augmenting paths. It computes this as the minimum cost solution for that graph. You say, great, how do I go from that to that? Well, clearly we have cut this unary cost. That unary cost is the cost of making A have a W equal 1. So we paid the price, so there we go, we get A equals 1. Here we've paid a pairwise cost of making A, what? Making A a 1, because it's this edge. Not the left going one, but the right going one. So we paid the price of making A a 1 and B a 0. So we're already hinting that we're probably going to make B a 0, aren't we? Sure enough, we're cutting this edge. We paid this cost, we make B a 0. And then we get here the same again. So if it's a correctly optimized graph, you could, to read it off and write down the solution, you could probably just look at each node and look at which unary cost was paid and just write that down. All right, so that's the 1, the 0, the 0. Or just to check, you could look at the pairwise terms and confirm for yourself that you're actually writing down the real state that you got here. And our overall cost, because of these 4 cuts, right, is 3 unaries plus 1 pairwise. Because we had one sort of change of state, right? We went from a 1 to a 0 once, and then we kind of stayed in the same W equals 0 state. So for, one more, but you get the idea, right? So this is a seemingly complicated cut because it goes through 2 pairwise terms. The result is, of course, as we read from left to right, we're changing state twice. But again, you can just read off the unary terms to figure out what A is, what B is, and what C is. So all the possible states for a 3-pixel image are illustrated here. And as pointed out, we have not worried very much about our pairwise costs when the 2 pixels have the same label, because we had initially defined that as being 0. Okay. Is that in any way confusing? Are there any questions? Can we? Yes, go ahead.
Can we ever get a contradiction?
You shouldn't get a contradiction. The answer is no. You can't get a contradiction. If you've done everything correctly, you can't get a contradiction. We're about to explore what one thing that could be incorrect in your setup that would potentially give you a contradiction. But as long as you meet the assumptions that I'm about to discuss, you won't get a contradiction. Yes?
What's a cut in terms of the image?
A cut in terms of the image. So we've got this is a pixel. These are pixels. So a cut means that whatever the x's for these respective pixels, A, B, and C, a cut between them is saying that on one side the world state is one thing, and on the other side the world state is another thing. Maybe just to remind everybody, our context, remember from Tuesday, is we were saying there's some likelihood, there's some possible function that you have that says what is the probability of x given w. Okay, that's great, that's important, but if on top of that you have a prior that says that your world states should be similar to each other, should vary smoothly, this is how we enforce this prior. This is us enforcing the prior, saying I want my neighboring nodes to have similar states. And so it happens this is a 3-pixel image, but we can have chains and we can have trees, but also we can have grids and loops. Right? And that's something we couldn't do with dynamic programming. Yes?
And by enforcing the prior, you mean the costs of the edge would be, we set them high.
The costs of the...
So we wouldn't cut.
The costs, I don't want to say the costs of the edges are high. The edges are designed to prefer...
Pairwise costs.
The pairwise costs are designed to prefer having the same state on either end of the edge. So if either end of the edge has the same state, either both zeros or both 1, then that cost is quite low. And it says, yeah, good. Let's keep them the same. It's encouraging smoothness.
Maybe let me rephrase it. How does our knowledge of the prior impact where we've gone?
We have a solution here that goes 0, 1, 1. With the unary costs, we were expressing how much does the data match the world state for A, how much does the data support a world state of 0. It's possible that this pixel in the middle was kind of on the fence. The data was ambiguous. Maybe the data here, so I'm just talking about the data, right? And I'm talking about a graph, which, if you recall, was, I was doing a grid, right? These were W, we could call it A, W, B, W, C, D, and so on. And then we were saying, those are all undirected edges, and then we were saying, okay, here's X sub A, and here is another X, and this one has X sub B. So we had undirected edges on the top between all the world states, and then we had directed edges for the data. So back to your question. How does the prior affect the answer we might get? Imagine that the data for pixel A was quite unambiguous. It said definitely world state equals 0. Right? Don't even try to change me. The last pixel similarly said world state equals 1. Definitely, what are we doing? Apple dot apple? Yeah? Okay, definitely not apple, definitely apple. And the data here in the middle might have said, actually I'm not sure. I'm really close to the boundary, right? So, in that case, it probably looked at its pairwise costs to both sides and said, which one should I go with? I've got to pick a state, 0 or 1, and which one am I going to trust? So, in our case, we're saying that the pairwise cost is the same for all zeros and ones being next to each other, and ones, zeros being next to each other. But maybe the unary cost here was just very slightly in one direction, or very slightly in the other direction, and the pairwise term here overpowered it. The pairwise term on this, between these two pixels, B and C, said, you know what, you should join me and be a 1 along with me. maybe this one wasn't as confident of it being not apple as this one was confident of it being apple. So the overall cut, the cut that had to take into account all the possible configurations of pixels, said, you know what, I can't afford to make that a 1 because the unary cost of because the unary cost of saying not apple is so high I can't overwhelm it. But this one, he's kind of a pushover. He's on the fence. You might as well make him just agree with this neighbor. So the pairwise term can overpower what the unary terms are doing. All right. So the approach so far is that we're associating our problems, our graphical models, with a minimum cut on a graph. If we can convert it into a reasonable graph, we compute minimum cut, we will have a solution. We just have to set the capacities on the graph so that they match our cost function, so they represent the values in our cost function. We use augmenting paths to find the minimum cut, or you could use some other graph cut type algorithm. And this is going to simultaneously maximize the flow or maximize the a posteriori solution. Because we're making sure to convert our costs, our unary and pairwise costs, into meaningful capacities. So we're not quite done yet. Because of the point that was made earlier, what about the general case when it's not free to put 0 next to 0? In other words, we now have a pairwise cost of putting a 0 next to a 0, and it's not trivial. It's actually some non-zero number. Same thing for configuration with 2 1s next to each other. So now we have some kind of non-zero cost for all 4 possible configurations. So we reduce our image now, we just have a 2-pixel image, so it's even easier, right? It's going to be the same setup as before, right? So we have unary costs. If this ever gets cut, that means A is what?
0.
A is 0. If this ever gets cut, it means A is 1. All right. But if we just left it the way it was, which was like this, then it was possible to do a cut like this, cutting that and cutting that. That would have made A,
0.
and that would have made B, and our total cost would have been 0, cost of A0 plus cost of B0, and no mention of this thing. Right? So that's not acceptable. We have to now incorporate, we have to throw these terms in there, that one and that one. Theta 0, 0 and theta 1, 1. So, trick to do that is we add in PAB 0, 0 onto one of the unary terms, and we add PAB 1, 1 onto the opposite one. We could have done it the other way around. We could have put this one, added it on here, and added this one over here, just as long as you do it symmetrically like this. Now, it works out. If I cut from here, we say, great, that's A is 0, we pay the unary cost. B is 0, we pay the unary cost. And we also pay the pairwise cost of making them both 0. Similarly, if I cut this way. But now we've created a problem for ourselves. Now, if I, for instance, were to cut not this way, but this way, then I'm going to pay the unary cost of making a B 0. That's fine. I pay the pairwise cost of making A and B both 0, but that's not right because I'm about to make A 1. So we have to subtract this off again here in the middle. You see, if I had left this as it was, which was PAB 1, 0, and I made my diagonal cut, I would have paid the 2 unary terms that I should have paid, UB0 and UA1, but I would have also paid unnecessarily high prices for AB being 0, 0, which it's not, and for AB being 1, 1, which it's not. So I have to subtract that and that off here in the middle. Okay, it feels a little bit like you're sort of plugging holes in a dam and then other holes are appearing. It doesn't go on like this forever. It does go on a little bit more, but not forever. Okay, so don't get too worried. With this fix, we're there. Well, now all of our pairwise terms are accounted for. They're all represented. Any valid graph cut solution for this is going to give you the meaningful combination of unary terms and pairwise terms that you asked for initially with your problem. Is there a question? Okay. All right. Now, reparameterization. There's a slight problem here. That was sort of my second bullet here. Negative costs. So, reparameterize. You see, we said our augmenting paths, our graph cuts, our algorithm that deals with graphs, our black box for dealing with capacities, it likes those capacities to be big or small, maybe 0, but not negative. And they weren't negative until we started subtracting things. Because we're subtracting things here in the middle, it's possible to have what were otherwise perfectly nice positive costs, and now they become negative. And so you might have a negative cost on this edge. And that's no good. So we need to reparameterize, which means that we're going to inflate our costs a little bit so that none of them are 0, so that not a single one is 0. So we can reparameterize in a few different ways, but we're going to do this by adding, for example, a constant alpha. So keep in mind that these here are our unary and pairwise costs directly from our probability representation, our graphical model with pairwise and unary costs. We can put them here as is. All right. To avoid these negative numbers, though, we might reparameterize so that overall a graph that looks like this suddenly looks like this. We add an alpha to this unary term and this unary term. We only had to add it to the A node, but we had to add it both for the source edge and the sink edge. Why is that? Well, you're going to have to cut one of the A edges, either this one or this one, right? You're never going to cut both. You're never going to cut 0. You're always going to cut just one of them. So if you had figured out that this is negative 7, I'm just making up crazy numbers, right? If you figured out that this could potentially be a negative 7 cost, then you can add 7 in the form of alpha here and here. So all cuts are now more expensive by the same number, by constant number 7. But if all costs have shifted by 7, is that going to change which cost is the cheapest? No, it's not. Everything's been inflated by the same constant, so what was the right answer is still the right answer, and we've avoided having negative costs in our graph.
So alpha is obviously equal to the most costly pairwise cost.
The most negative combined pairwise cost. So in this case, it might have been that these were all quite small, right? But in total, this got quite negative. Yes?
Did you leave the pairwise minuses out of this image?
Yes.
But they're there.
They're there. So we were saying we can now, yeah. So I left it out of this image.
Okay, but introducing alpha doesn't mean that they go away.
It doesn't mean that's correct. Yeah, that's exactly right. So reparameterization is to fix the problem of the negatives. It doesn't fix the problem of, well, you need to pay the right pairwise costs every time. Yes. Was there a question? Yes.
Yeah. So we should not have these negative costs because we add them up together. So we will lose information.
Will we use? I don't know about losing information, but the augmenting. I don't know what augmenting paths does with negative values. I think it doesn't. I don't think it works. It is not guaranteed. I know that it's not guaranteed to give you the optimal solution if you have negative costs.
You can go in circles.
Just comparing.
I guess you have somehow. I think you were asking last time about the total of the flow. If it's someone was asking this question, so yeah, maybe it goes in circles. I don't know. I don't know what happens. I just know it's not guaranteed to converge, so I've never done it. Is that a satisfactory answer, or was there? Because I kind of cut you off.
It just kind of seems to me that at the end of the day we have like a matrix of pixels and we come up with numbers. We compare them in relative ways. So I mean, like, does it matter if they are slightly more?
So we have input of pixels and we have output of states. And so if we have negative numbers, we might end up choosing states that are less than optimal a combination. Given our data that we've observed, given our pixels that we've observed, it might be that the right combination is for A to be apple and B to be not apple. That's the overall joint configuration of W1 and W2. If you arrived at a suboptimal solution with the graph cut, then you might mistakenly think that one of the pixels was apple when it shouldn't have been, and that's very bad, right? That's what we say. Oh, that's very disappointing after all the work we've done. Yes.
I think that there's just no mean to negative costs, because what's the capacity? What does negative flow mean? The flow isn't direct. So if you said -10, still 10 units of water, let's say, would pass from this node. It would be like saying +10 to the algorithm, to the way the algorithm works. They have no negative capacities, have no meaning.
It would be potentially a reward system rather than a
Yes.
penalty system.
Yeah, it would be like having a positive.
I guess in the interest of time, I'll say I don't have a good explanation for what happens if you go negative with the costs. I've taken it on faith so far not to do it. Maybe because the flow analogy was so convincing. Mostly, I think I was just lazy. So I'm gonna. If there are more questions, yeah, go ahead.
Different question.
Yeah.
Why do you add alpha to, say, 2? I thought you added the smallest value onto all of them to build up by the smallest value.
We are certainly allowed to add something else onto this side if we wanted to, as long as we add the same thing here and add the same thing here. However, as long as alpha was big enough to raise our most negative cost into the positive regime, then there's nothing gained by inflating the overall cut cost any further.
So you only need to do this for, so if, say for instance there's a negative cost somewhere on A somewhere, connecting it to either a source or a bit sick, then you need to add something that you wouldn't need to add it onto any of the other.
Correct.
Source or sink.
If we had 100 pixels in a row, and there was a negative somewhere between pixel 99 and pixel 100, that was the only negative, I could still fix that by just adding alpha over here on pixel number 1, because every cut that looks at all of the 100 pixels is going to have to go through either through this edge or through this edge. It might do crazy stuff later on, but it will always go through one of these two. So I only have to augment one of them with this reparameterization. Okay. Okay. Now, this is as bad as it gets in terms of reparameterization, and then soon we'll be able to press on. Let's see what we're doing first. All I've done here is done a very similar reparameterization, except instead of adding alpha here and here, I've added, so that would have been on the unary cost for the same node, I've added a beta to the unary costs on opposite nodes, subtracted it in the middle, and added it here. Okay, seems more complex. Indeed, this is a more complex reparameterization. The reason we introduce it is so that I can show you how this reparameterization dictates to us, it tells us what are acceptable cost functions. So while you might normally do the reparameterization with the alpha that we just discussed, this is a valid reparameterization which allows me to prove something to you. Okay. Before I do, just confirm for yourself, right? If you were to get 0, 0, so a cut that goes here, right? You'd have a cost that was inflated by beta. That's fine. Here you'd have a cost that's inflated by beta. Or if you went this way, you'd have a cost that's inflated by beta, then deflated by beta, because we'd be cutting, right? If we cut this, that means this is a 1. Sorry, this is a 0, so we're in the 1, 0 configuration, so we're using that arrow. So plus beta minus beta is 0, plus beta, so inflated by beta. So you should see that we are still giving the exact same solution as we were before. All we've done is that we've added the beta on opposite sides, and then had to subtract it here and add it here in order for all the same terms to work out. Okay, but why is this reparameterization noteworthy? Okay, it's noteworthy because we come back to what we said is the necessary step when you have the general case. The general case meaning you pay some pairwise penalty, some pairwise cost, both for putting a 1 next to a 0 and for putting like with like, for zeros and being together or ones being together. Remember this one? We said, okay, now we've got this PAB10 minus the 2 like with like terms. And adding the like with like there and adding the like with like there, right? So you've seen this picture before. But to do our reparameterization, we have to subtract the constant beta from this term and add the constant beta to this term. Yes, there's a question.
Just we're wondering about the frames here. Why are we punishing both putting like with like and like with like together?
You might
Why
have
punish both cases. When can you get it right?
When can you? So you can always get it right, but there might be some reason that you think that the edges, that the pixels should have not a free ride if they are side by side and they are the same. So you're basically, if you say being like with like is 0 cost, then you're limiting how much you're limiting the opportunities to put like with dislike. You're saying, okay, it's always cheaper to do this, but in fact maybe they're actually quite close to each other, right? And you want to put 0 and 0 being together as a cost of 0.5 and 1 and 0 being together as just 0.6. You only want a difference of 0.1 there. So you could achieve that difference of 0.1 even if we left like with like as 0, right? But remember, the unary terms are also competing here. So the unary terms might have an easier time. This is a slightly more involved answer, but if you're still following me, that's great. The unary terms might have an easier time of influencing things if the like with like term is non-zero. Yeah? It's not the same configuration to have 0 versus 0.1 in the pairwise as 0.5 versus 0.6. Okay. So we can subtract our constant, we have to subtract our constant beta there, we have to add our constant beta there. If we do that, we have two new equations. We're basically saying we're going to subtract the same beta from this that's this here, and it's going to be greater than 0 when we're done. So we're going to choose a beta that makes this true. And you also have to have pairwise costs that make this true. Similarly, for this second equation, if we take PAB 1, so that's theta 1 plus beta, that also has to be greater than or equal to 0. So we've got these two constraints. We've arrived at these two constraints just by virtue of doing a reparameterization, which hopefully we've all accepted. It's still just the same problem we started with. Now, we can add these two equations together, the betas go away, and what we're left with is this equation that says theta 10 plus theta 1. So the two dislike costs added together minus the two like costs in total have to be greater than 0. This doesn't sound very exciting, maybe, but the point is that now we know what are valid choices of theta and what are invalid choices of theta. If we want the graph cuts algorithm to converge to a meaningful solution. So, will it ever choose the wrong answer? If you obey this law, it won't. So, this is the definition of submodularity. If this condition is obeyed, the problem is said to be submodular and can be solved in polynomial time. Polynomial time because our augmenting paths takes polynomial time. If you don't obey this rule, then it's NP hard. NP hard essentially saying you have to try all the combinations of 0, 1, 1, 0, 0, 0. You have to try out all the combinations, compute the cost of each combination exhaustively, and then see which one was the cheapest. So we don't like that. That's incredibly expensive when you have a megapixel image. We do like this, right? So if you can, choose your cost functions so they obey this rule. Okay, now if you apply this this kind of regularization, i.e. we're implying a smoothness on our prior. We're saying world states. We like it when pixels neighboring each other have the same world state. There's some very small non-zero cost for having the same, for having a 0 with a 0 or a 1 with a 1, but it's much more costly to change state. So, if you have a small pairwise cost, well, this is the original image. If you have a small pairwise cost, this is what it looks like. So, some of these black pixels have turned white, and some of these white pixels have turned black. If you crank up the pairwise term, we had a pairwise term in the dynamic programming as well. If you crank up the pairwise term a little bit more, you should be seeing that the pairwise term is starting to outshout, to dominate over the unary term. Remember, the unary term is always sitting there saying, I'm looking at the data. In this case, the data happens to be pixel intensities, right? I'm looking at the data. I'm quite happy being a 0 or a 1. I'm happy being a 0, let's say. And the pairwise term is gradually sort of using more and more force to say, no, you should just agree with your neighbors. Whatever you think you saw in the data, agree with your neighbors.
So why is H completely white? Is that because there are more
That was
white?
going to be my question, and that's indeed the answer. Before I cut you off, someone who didn't hear him, why is the final solution here, when we've cranked up the pairwise costs really high, why is this white instead of black? So I'm looking for the back rows because there's a less of a chance that you heard the beginning of his sentence before I cut him off. Yes? There were more white pixels in the first place than black. So, if we were going to agree that everybody has to be, we like it when everybody has the same world state, the unary costs got to express that little bit of opinion. They were listened to just enough to say, well, okay, if you're going to choose one color for the whole image, for all of these random variables, Can it at least be the one that makes the majority of us in the original image happy, right? The one that corresponds, that agrees with most of the likelihood. The likelihood being comparing W to X.
I don't think I'm seeing the whole picture, but how big is the neighborhood in this case?
The neighborhood for each pixel here, this should be a 4 connected grid. Each pixel is connected to its east, west, north, and south neighbors.
So, but in that case, I know there's sort of there's going to be a relationship between pixels, but how is each pixel, as you are looking at it, how is it aware of everything else? I know that's kind of why we're doing this, but from one pass, I don't quite see how you would get all that information together.
So one pixel is here. It's a single observation of some grayscale value. The site, that is the world state associated with that pixel, is connected to its neighbors.
Yeah.
And it's saying, well, based on the costs you've defined, how more or less intensive, we are going to have to agree on our world state, or it's okay to disagree. That's maybe I need an edge here as well, right? So connecting this one to all of its neighbors, all of its first order neighbors, not connecting it with pixels 10 away. So that is the context. It's trying to make it would be making its own decision in isolation of everyone else if we were doing it like we did with the Apple assignment, every pixel independently. It would just look at the X and look at the likelihood, and it would say Apple, not Apple. But now it's saying, okay, well, Apple or not Apple, weighed by the fact that my neighbors are telling me things. Yeah?
What I mean is in H, for example, if the information is first order neighbors,
yeah,
everyone gets their first order neighbors, then how in one pass you get the idea that there were more white pixels in the image as a whole as opposed to black ones? I can understand how that works on a local level,
yeah,
not on the whole.
Okay, so we're talking about a pixel here. Let's talk about a pixel here, but it's at the location that was originally a black pixel. So it was saying, if it just looked at its neighbor, it was saying, oh, I should stay black. And it looked at, it had a distribution. It has a probability of being black, it has a probability of being white. But we look at the neighbors and we say, if this is black, it's going to pay a penalty because this one wants to be white.
Yeah, sorry.
Can you guys keep it down? It knows that it's got to pay a penalty. This one's going to be black or white. This one's going to be black or white.
Yeah.
It knows that it has to pay a penalty. It pays a bigger penalty for being different than that. It pays a smaller penalty for being the same as that. And that's repeated at all the pairs throughout the graph. Every one of them says, well, I don't know who we should vote for in the next election, but I just know that I want to agree with you on who we vote for.
Why I always the guy?
Because you're sitting right here. I can pick on him, but he asked the question. So this is if I'm going to vote either way, maybe I have a preference a little bit, but I just know that we have to agree, and he has to agree with her, and so on. Then it might be that eventually, because the whole back row has agreed to vote for one candidate, that all the rest of us switch to that candidate. Yeah?
It's because we're no longer going across in rows, say, we're looking at the whole thing at the same time as this grid.
That's the hard part. Okay, but it is, in a way, because you're talking about the first pass, and that's maybe the thing that I really hope everybody gets. There's only one pass. We're finding in polynomial time, we're finding, bang, the optimal solution. We're saying, without having sort of do passes, dynamic programming, forward or backward. No, all at one go, we can say, what should this choose in order to best agree with all of its first order neighbors, so the first order neighbors agree with their first order neighbors, and so on, and so that everybody agrees with their respective data terms. So it's like this sort of instant voting, this instant agreement. Okay, let's all just pick the right answer right straight away. All right. So let's see how we're doing for time. We are slightly over. So I will explain one thing, because we've just been talking about submodularity, and then we'll go to the lab. So I'll skip ahead a few slides. We will come back tomorrow and do the applications of this. And that means that we might have to read the chapter 13 sort of in our spare time. So we'll talk about that tomorrow. Submodularity, we had, this is using a slightly different notation because we've skipped a few slides, but we need a total of our pairwise costs to add up to something greater than 0, all right? Just to think of the betas instead of this particular equation, right? But essentially this is the same one. Now, we might have more labels, and that's the thing that we're skipping right now. If you have an abundance of labels, you might have different states, alpha, beta, gamma, and delta. And they still have to respect this greater than 0 rule. So, submodularity being greater than or equal to 0 means that if you're going to have, let me do it on this slide, and that'll be the one we wrap up on. If you're going to have two states that are different from each, if you have two states whose difference is 0, you should have a small cost. If you're going to have two states whose difference is big, so it gets maybe more positive or it gets more negative, but it's further from 0, then you want the pairwise cost to go up, up, and up. The bigger the difference, the higher the pairwise cost for M and N. Is this graph, the one here on the left, is that clear? Small difference between the two world state labels versus a big difference between the two world state labels. All right. Now, if the curve looks like this, the pairwise cost curve looks like this. This is a quadratic function, right? So it just has this kind of shape. It's nice and convex, which is nice. More importantly, this is submodular. Yes?
Our labels here primary.
So our labels previously were binary. We skipped in a few slides, having instead of 2 classes, multiple classes.
So how can you take the difference if you have an order like in order of similarity, like apples, pears, oranges?
Yeah, you can have grayscale intensities, right? You have 255 discrete grayscale intensities, and you're going to put 2 pixels side by side, and you're asking whether that's costly or not. And if so these are 255 categories instead of 2 categories. Okay, I don't have a good answer for apples versus, are apples greater than oranges? Okay, but I do for intensities, and I can say bigger difference in intensities should mean a higher pairwise cost. Here, you've got a submodular cost function. It's convex. You can go from any point to any other point, and you're never actually crossing through the function. This truncated quadratic doesn't behave that way. This one says if your labels are the same, you pay your pairwise cost is essentially 0. If your labels are a little bit different, you pay the same cost as if they're a lot different from each other. So it's like the quadratic up to a point, and then it's truncated. It just stays the same.
So if your cards, for example, that'd be quite good because it's tunes. It's expecting a change almost at a certain point.
It's expecting a change, and any further changes, you don't pay extra penalties for this. The cards is one, but I'm about to show an even better example of why you might want that one. Yes?
So convexity guarantees submodularity.
Convexity guarantees submodularity.
The other way around?
No.
No.
Does non-convexity guarantee non?
No, I mean, does submodularity guarantee convexity?
I don't know. I don't think so. Okay. And finally, the Potts model. The Potts model doesn't even try to have this intermediate state. It just says if you're the same label, you have no pairwise costs. Everybody else pays the same cost. Right. So the reason that's important, the reason this is the thing to remember about this is if you're given this type of noisy image and you use a nice quadratic function, which is great because it's submodular and you can use graph cuts like we just talked about. What it does is it prefers to make multiple little changes in state. So what you want is this sort of thing. You want this to be gray, and then a sharp boundary, and this to be white, and then a sharp boundary, and this to be black. That would be a good denoising of this. Instead, what we're seeing is this fuzzy denoising. Because it's saying, you know what? I don't think I can go from gray to white in one big step. The quadratic function is going to penalize me a lot for that. But I can make lots of little steps in intensity. And if 2 or 3 of these in a row allow me to gradually go from gray to white to black. So we're introducing this sort of fuzziness which wasn't there before. So I'm putting you in this tough spot because I've told you submodularity is great, allows you to use the graph cuts that we just talked about, but it means that you have to use certain cost functions which obey this greater than 0 rule. The downside is then you will introduce this kind of smoothness. So when we continue our lecture tomorrow, we'll talk about how to deal with cost functions that are not submodular. All right. Let's see everybody in the lab. This time, who's starting late? The people at the beginning of the alphabet? Yes? So I think we can get away with just 6 or 7 people hanging back a bit with coming to the lab. See you all there where you'll be working on grids. Yes?
What if instead of function like class,
Much easier now. You're welcome.
don't make it
Always count on
sharp, like
Count on me, you're always.
You're okay. That's okay.
will it give us a result?
As long as it's still, as long as it's convex. The convexity you can test by checking the second derivative. If it's convex, you go for it. Oh,
So, for example, when the test rate has been slight amount, picking up
the amount isn't so slight because you'll have to. What are we looking at? We're looking at this, right? So if you have to here, that has to be. Remember, I have to be able to get from here to here without crossing through. So I have to be able to go at this one. It basically has to go up all the way up here. Yeah? Hi. Sorry, I'm in the way.
Yes,
I'm
you are.
so sorry.
Glad you said it. I've worked a bit more.
Very sorry.